While we make the shift and set up for our next presentation, I'll take a minute to tell you about our next presenter. Bryan Barton is also using a genetic algorithm, and he's going to be doing it in a very different way. He's going to be exploring how we can sort of evolve robots to see if they can cover a large distance over different or over a particular type of terrain. So, genetic algorithm in a very different context here. Okay. I can stall it. Okay. So, genetic algorithms for designing robots and evolving robots to actually do some interesting things. So, Bryan, go ahead.
All right. So, it looks like for everybody today that you're going to get a crash course in a lot of machine learning. So, as Dr. Hugan mentioned, yes, I'm doing genetic algorithms. They've always been very interesting to me, especially. So, the field of machine learning is interesting to me because it has almost limitless potential. We can take machines, computers that you normally think would do kind of a static function, it computes something, and we can make it do more dynamic things. So essentially you can make computers learn in a similar way to the way we do. So what am I going to be talking about? I get a brief introduction on why exactly I chose the project that I did, and I'm going to talk about how we structure the robots, and how the genetic algorithm is going to interplay to change the structure of those robots to try to teach them things, or to have them progress in evolution. We're going to talk about the results I got, a few conclusions about why I got the results I got, and how I can improve the results. And then, of course, the project demo. All right, so moving on. My inspiration for this. A few years ago, me and our friends were just kind of surfing around the internet, and we found this thing called Boxcar 2D. And what it does is it takes these polygons, and it kind of randomly arranges the polygon by changing how long the sides are and things. And it sticks some wheels on it somewhere, and it drops like 30 of these in the same place. And then they all try to go forward and move forward like cars. And it was really interesting to me because as time went on, it would take the ones that did the best and it would kind of put them together and mish and mash the parts together until it finally kind of converged to this point where they were all getting about the same distance. So you would watch these cars learn over time. So I'm like, all right, that's pretty cool. What can I do with this? What if I could do this in a 3D world? What if I could do it with robots? So we moved on to robots. What do I want to do with the robots? Let's try to make them fly. You know what? We've had a lot of flying things. I mean, they have the quadricopters and things like that, so maybe not. Let's make them swim. I don't know much about hydrodynamics, and that might be difficult to simulate. Space navigation. Maybe I'm taking too many things out of the equation. There's nothing in space. Walking. Well, that's pretty hard for me to do sometimes, so I think walking might be a good thing to try to simulate. So I was excited about it. I told everyone, I'm like, yeah, I'm gonna make robots, and they're gonna learn from themselves to improve themselves over time. And a lot of people's first reaction is, are you trying to make a new Skynet? And I'm like, well, yeah, kind of. But first, I just kind of want to get them to move around. All right. So genetic algorithms. So here's your crash course number 2. How do they work? So we start with the genetic algorithm. It generates a bunch of robots completely randomly. So it just puts a bunch of parts together, a lot like the cars. So 90% of them won't really do anything useful, but a few of them might. So those few that do well, we give them a good rating. So we start out with a robotic list, and each robot gets a rating, and then we take those robots and we put together the ones that did better. So take robot A and robot B and kind of splice them together and see what we can make out of that. And then we generate a new set from all of this. So now we have a new set of robots made up of our previous robots, and what do we do with those? Well, we throw them back into the fitness evaluation and have them try to walk or do something interesting. All right, so what's a robot made of? We start with a small component, which it's like a metal bar or a 2x4 or something like that. It's very simple. It's a very simple primitive structure of the robot. We take that piece and we connect it to other components with a joint. A joint can be either static or dynamic, meaning that it's either a very rigid connection or it's one that can move back and forth like an actuated joint. And those move on a very specific angle at a specific rate, so they go at a very specific speed. They're all the same amount of speed, and they're all the same amount of strength as well. It's kind of like muscle strength, for example. And we connect those into each other until we get what I call a group of units called functional units. And functional units, it's a grouping of units that perform some sort of function. We may not know what the function is, but to the genetic algorithm it might. So for example, my finger, like one finger may be an example of one component, whereas my entire arm may be a functional unit because it performs some sort of function. So the point is to make these things modular so that we can take them and connect them into a robot. So this would be an example of a robot, or a blueprint as I call it. It's composed of 3 different functional units. So quick recap, we have a component, and many components make up a functional unit, and then many functional units compose a robot. Alright, so why? Why would I do that? Why have this functional unit? Why is there a middleman in there? A middleman usually is a bad thing. Well, in this case, it's so that we can reduce search space. And what I mean by that is that when the genetic algorithm is going through and is splicing and connecting all these different parts of a robot, I want it to be able to make fairly large changes so that the convergence into an optimal solution goes a little bit quicker. So for example, if I had a robot composed of 1,000 components, switching out 2 components may not make a big difference, but switching out 6 components or 3 components may make a bigger difference, and at the same time, if it's a useful functional unit, that may be a change in function, and not just a change in an individual part. Alright, so assembly, how am I putting these things together? So we have the components, of course, that make a functional unit, and what I'm doing is I'm taking 3 components, and I will connect them at 90-degree angles, and I create every single permutation of those. So I create this huge library of functional units for me to use. I can just pick from the library to select a few to make a robot. So I generate all possible of those, and then I take the functional units and I make a robot out of them. So if we can imagine every box up here being a functional unit, we first place the initial functional unit in the middle, and then we say, okay, the next one can be placed at 1 of 6 places beside it, much like the sides of a die. So then we would place the next one, and then say we want to place another functional unit. Well, it has the possibility of randomly going in 1 of 10 places, because of course there are 2 places taken up by the current functional units. So we just randomly select them and build them and put them together like that, and we end up with these really weird random robots that do some weird stuff, and you guys will see those later. So now that we've got our random robots, how do we evaluate how good they are? Well, I place them on a flat terrain. Well, in this case we have a flat terrain. And we sit there and we just throw them down and we see how far they can walk, or how far they can crawl, or whatever kind of function they seem to do. So how far they can go in that direction, we rate them on how well they can do. Now, if you may have noticed earlier, my title said multi-terrain, had the word multi-terrain in it. What's that mean? Well, that just means I'm going to be testing them on multiple different terrains to kind of find the one that can perform the best across all different terrains. So as kind of a proof of concept, we have another terrain in here, which is just an uneven terrain. And if we zoom in a little bit, you can see that it's quite uneven in several different places, which actually can present a pretty big problem to some very, very simple robots. Alright, so parent selection. So we've evaluated how well they've done. How do we select which ones that we're going to use? Well, we have this list from before of these robots that have been evaluated on how well they do. Now let's give them some numbers. So let's say that they are rated from up to 90 to down to -10. Well, our first task is to change all of their fitness scores to a value between 0 and 1, or basically normalizing the scores. So first step, let's add 10 to all of them, because our lowest scored robot is -10, so we don't want negative numbers. And that leaves our highest scored robot at 100. So now let's get it to between 0 and 1. We divide them all by the highest scoring robot of 100. So we end up with scores between 0 and 1. So now how do we select which ones we want? Well, first, we randomly select one of the robots, any robot in there, doesn't matter which one, and then we generate a value between 0 and 1. Now that value determines whether or not that robot that we've selected is going to be accepted as a parent. So you can select them, but they still have to be accepted. So if you think of, I guess I should note that the random value that we've chosen between 0 and 1, if it is below the score of the robot, then that robot is accepted. So if you think about it, Robot 2, for example, would have about a 50% chance of being selected, whereas Robot 3, who didn't perform as well, would have about a 30% chance of being selected. So let's go and look at this a little bit closer. So let's say that we select Robot 4 and we generate any number. It doesn't really matter at this point because the score is 1. Everything's going to be below 1, so Robot 4 gets selected. And say we randomly look at Robot 2 and we say, okay, we're going to accept you. Say we generate the number 0.65. That's above 0.5, so sorry Robot 2, we don't select you. So we look at Robot 1. I'm sorry for the ordering, I realize it's kind of confusing now. Anyway, moving on. And say we generate the random number 0.35. Oh, that happens to be below 0.4, so we select him. So why would I want to do this? Because obviously Robot 2 is better than Robot 1, right? So why would we want to splice one that may not be the optimal? Well, that's because we want to introduce diversity and variation into our robots. So if, for example, Robot 4 and Robot 2 are both very similar in how they were made and what parts they had on them, then that means that they may be converging to a local maximum in their or in their scores. Whereas maybe robot 1 has some sort of unique trait that may not be, or has many unique traits that aren't as good as the other two, but one that's very good. So it's a good idea to kind of include variation in there so that that one unique trait can maybe shine through with some of the better robots to produce better children. Alright, so we selected the robots. What do we do with them? Well, we want to do a crossover technique, which is just to take parts of one robot and switch it with the other. And this part is actually quite simple. We just select 2 random functional units on here, and this is where the modularity of functional units comes into play, because we can take these units and just swap them very, very easily. So we swap them, and if you watch very, very closely, they switched. So these would be the 2 children of those 2 parents, and then they would be put back into the new population that will be evaluated, and then this entire process repeats. So, quick overview of what's going on in my project. We randomly generate the robots, we test them, so here you can see a testing area on both the flat terrain and the uneven terrain. So this area right here is actually a huge column of about 25 different terrains and 25 different robots that are sitting there trying to move somewhere. And then we take them, we evaluate them by average, so say a robot did 50 on the flat and 30 on the uneven terrain, so we average those together to determine their score, of course. And then we select the parents, and we produce the offspring, and it comes full circle. It's a very cyclic process, and we do it all over again to try to find an optimal solution to, well, walking in this case. Alright, so what were my results? I didn't realize it was going to be this bad, but if you squint a little bit, you can see the high raw score in blue. And you'll notice it kind of looks like a heartbeat. It goes up and down very far in the graph. And there's a few reasons for this, but as far as I can tell, it seems to be kind of errors that I encountered just with Unity. But anyway, I took that and I said, well, I want to have a different view of this, so I ended up doing a fitted raw score, which means I take a point and I say, well, this is the score of the highest scoring robot, and I take the average of all robots around it to kind of fit it to a graph. And you can see that the best of the best robots, they're improving over time with the red line. So they're kind of improving. You see near the end it kind of plateaus off. This is where they've all converged to being about the same type of robot. So this is the point where they've converged to about the same. And if we look at the green line, this represents the average score of all robots put together. And this one is not to scale, so don't think that the average is actually better than the best. But anyway, if you note on this, it's actually improving as well. So not only is the best of the best getting better in these generations, but also the average of the best is increasing as well. So the entire population is actually improving. So I learned that small changes have a big outcome. Changing, for example, just the strength of the actuated motors, for example, changing that changed the form of the robots almost completely. Changing how many units there were is very important. And even changing how many units I was testing at a time seemed to change the results, which is quite interesting. And muscle strength. I found that muscle strength was a big factor in this as well, because if it was too high, they would just kind of flail about and do crazy things, but if it was too low, they would just kind of lay there. But I had to kind of mess with that and get it just right so they would produce something that looked natural. My goal was to create things that look more natural, something that maybe could be actually produced in real life. And having few units I found to be kind of a bad thing as well, because for example, if we have 2 robots that are made up of 3 functional units each, and we swap those pieces, then that's a 30% change to the children. That's a very big change. And it's not as gradual as you would think evolution would be. Elitism selection. So I tried out taking the best of the best and allowing them to move on. And I noticed that even though they hadn't changed per generation, and you can really see this in the raw high scores, that you would think if the best of the best is allowed to move on, then it should perform the same every time, which means the graph should never go down. But for some reason, I actually received results that went down, and it didn't make a whole lot of sense to me. Physics errors. I found that, turns out, genetic algorithms are actually better at finding errors in your code than you are. They somehow figured out how to make the functional units spawn within one another. And in Unity, the engine that I'm using, when they spawn inside of one another, they start having physics collisions that aren't really calculatable, which makes them kind of fly across the screen. And guess what? When something flies across the screen and goes, 1,200 meters, all of a sudden that one gets a good score, and that's bad for what I want. But of course, Unity thinks it's good, the genetic algorithm thinks it's good, so you end up with tons of them that just kind of catapult themselves for no apparent reason. Robot form. So I don't have a way to actually change the form of the robot built into this. So for example, if a robot was in an L shape, and we spliced it with the parents, it would still remain in an L shape. It would still have functional units. It would still have different functional units within the L shape. Is the only difference. And I found that using elitism and taking one of the best and letting him move on was actually skewing it so that a lot of the robot forms were appearing as the same form, and then near the end they kind of plateaued. So that's a reason for the plateauing that we've seen. So here we have an example of a robot during the later generations. This is about generation 65 or so, where they discovered my error in the code. So if you notice, this thing flails wildly. So you're watching this robot and you're like, oh my gosh, what's it doing? This isn't something that we could reproduce in real life. This is a complete physics error, and it's absolutely terrible. So that's just an example of one of the errors that I ran into. All right. So conclusions. Why did I get what I got? I don't think that this is quite the most optimal solution for creating walking robots. Mainly because they actually converge quite quickly. I said that the previous one was actually generation 65 or so, and generally things don't converge that quickly in a genetic algorithm. So this means that they're most likely finding a local optimum to kind of sit at. So it finds the closest height it can get to, or the furthest it can get, and all the robots kind of converge that sort of walking to get there. And the joints don't move intelligently. So I said earlier that they move at a specified angle, at a specified strength, at a specified speed. So they don't move intelligently, they're just kind of mashed together that way. And I feel like that's maybe a reason that they don't converge or do converge depending on what they do. And of course the static robot form, which I mentioned earlier, it will always stay in an L shape no matter what. It will just simply have different functional units in those places. And unity is unpredictable. I mentioned that, the fact that even though the best of the best got to move on, they still got different scores. And that was quite odd. Oh yeah, I'm sorry, I've been talking about Unity this entire time. So Unity is actually a game development platform, but it has a pretty good physics engine in it. So I actually used Unity to put all of this together. So it kind of runs the entire thing. It's what actually runs the simulation itself. It's the engine that I'm working with. Anyway, so I believe this is actually a step in the right direction though, because I feel like there are many things I could do to improve this to make it quite good. And the first thing that I would like to do is, like Paul, implement a neural net in this thing. Because, of course, joints don't move intelligently, but if they could, then we could take robots, and no matter what their form, they could learn how best to move their arms and legs around, so that you get the best solution out of a specific robot's shape, is what I'm trying to say, I suppose. It would be like if I hadn't prepared for this presentation and somebody tried to evaluate me on it. That wouldn't be a very good thing. Fill in the spaces. So you may have noticed that some of the robots that I've shown up here, they seem to have awkward spaces in between the functional units, and that's one thing I would like to correct. So I would like to put parts in between those spaces to try to improve it. I feel like it would just be a better representation of robots that we can produce in real life. Discard the unnatural ones. I told you that it found errors in my code that I couldn't find, or at least I have yet to find. So maybe trying to prevent them from spawning in one another isn't the best solution. Maybe we should just discard the ones that have done that. So just give them a negative score when you detect really crazy physics collisions. And I believe it needs a mutation algorithm to try to solve the L-shaped problem. So for example, maybe we'll take a functional unit randomly and move it to a different side. So that'll change the overall form of the robot. And finally, more terrain types. I had the uneven terrain type in there as kind of a proof of concept, but I would like to implement more. Just so we can get maybe more variation in robots, or maybe just more robots that have the ability to travel across different, lots of varying types of terrain, more multi-terrain, I don't know, like an ATV, I suppose. And symmetric robots. I've read a lot of studies where robots, no matter how you generate them, almost always end up being better if they're symmetric. So I feel like mirroring the functional units across it would also be better. And you'll actually see later when I get to the demo that they did do that. A few of them actually turned out quite symmetric, at least the best ones. So at the end, I always like to go through a lessons learned thing, and this is really a lot for the people who are starting to become seniors and they're going to go to a senior seminar. So to start off, look ahead and experiment. I chose my tools, and early on I actually ran into a problem with them. So try to play with the tools as much as you can. Even if there's something that you assume is going to work, test it first to make sure, so you don't run into roadblocks. And avoid controlling evolution. Throughout my project, there were many times where I said to myself, that robot's not really turning out the way I thought it would, or this group isn't turning out the way I thought it would. And I tried to change things, but I don't believe that was a good thing to do. And in fact, I feel like you should just let evolution take its course. And don't be afraid of change. I mentioned earlier I ran into a roadblock. I had to change my seminar because of it, slightly. So if we look over here, we can see 2 blocks, and there's an arrow. This means that I wanted to pull the blocks apart and push them together. My original idea was to put hydraulics into this rather than the actuated arms that I've been talking about. It turns out that's incredibly hard to do in Unity. There's no built-in mechanics for it. I tried to do it myself, which wasn't the best thing to do. And I spent like 2 weeks on it, so I should have just moved on. Start early, save early. There were many times during the early stages of this where I would get a little bit of work done and I wouldn't save it. And then I would do it over again. And it didn't seem like much at the time because I hadn't gotten very far, but I'm sure that added up in the end. There were probably many hours lost because of the small little things that I forgot to save. Set waypoints and work time. This is a self-run project. You have to do everything yourself. So set some time to sit down and work on it every time. And set some goals for yourself that you want to get completed during that time. Alright, so as I bring up the demo of this thing, are there any questions? Oh.
Were you considering using anything else besides Unity? Or if so, would you still have chosen Unity knowing what you know now?
I looked into, I can't for the life of me remember the name of it, but this was, hold on, it's maybe open already. I'll open that one. Sorry, Paul. It's being a little bit. Alright. So what you're going to see right now is the first completely randomly generated set of robots. Alright. Anyway, yes, I did look into a couple of them. And one of them I found actually did use servos, like you would see in a regular robot instead of the actuated joints that I'm using. And I liked how they looked. However, it seems like a lot of them, they're very, very static. There's only a few things you can choose from, and I really wanted a way to kind of create my own robots. So I probably still would have stuck with Unity. However, had I been more familiar with a different engine, I might have gone with that as well. So yeah, anyway, these are completely randomly generated. As you can see, they're just kind of flailing about, and they're not really getting anywhere. So their goal actually is to move that way. So that one kind of looks like it's not doing bad. So this is the randomly generated set. Now, pause for just a second. I'm going to bring up a set that has gone through just about 200 generations. This took about 3 days to do, give or take. Script. All right. So there's a few of these, but you'll notice that many of them are actually they do some odd things. So many of these are actually turning out symmetric, even though it's not something I built into the program. That one is by far one of my favorites. This one as well, but they work pretty well, honestly. Like, they're moving forward like I would expect them to do, much better than the random flailing that you saw in the very first generation.
Brian, it does perhaps seem to resemble early evolution as in a worm.
That big useless part. Drag that thing around. I wonder when you talked about having errors in some of the good ones being errorful, you'll notice now that thing is moving sideways. So if for example, that had moved just directly across, it would get a much better score than if it went sideways. So maybe a lot of you, this is happening to you a lot of your creatures are getting a good score once and then therefore being chosen, and they aren't that good because now he's going backwards.
Yeah, I know. That was actually a big factor of the runtime. So I extended the runtime on this one. Normally they only run for about 60 seconds. So that one actually would have already disappeared. So by the time it started turning around, it would have seen that. So normally he only would have been evaluated for just about how far he got before he turned around.
And the other thing is that I wonder about is they've got symmetry, or the beginning to get some symmetry, but is there any way for the GA to recognize that, to coordinate, that is, to use two parts that aren't directly connected together, to recognize that that's a useful thing. I mean, there's no way to reward that, I think, other than happenstance. But these two things should be whipping around at the same time.
Yeah, I think that's part of where I would like to build in a neural net to
There
it.
may be some,
Yes, Ethan.
Did you consider, I think you're measuring just how far they made it in one direction.
Yeah, it's only based on the X value of the robot.
Did you think about how much they spent, how much time they spent going in circles or going left or adding that into it?
It is
something plausible?
purely distance from the starting point.
I was just wondering if that's something that maybe in the future.
So at one point I thought that it might be a good idea just to reward them on moving. You know, maybe if you just don't sit in one place, that would be great. And it seemed like a very promising idea, except for I realized that, well, if one decides that it's going to go right and it does really well, and the other decides that it goes left and it does really well, and those end up being, you know, two parents that are very viable candidates. But maybe when they're spliced together, they just sit there because they both had parts pushing in the opposite direction. So I was thinking that maybe it would be a good way to maybe cut it into cardinal directions. So for example, you know, maybe if a lot of them go north, then you take the group that goes north and only work with those. So it's potential. I did think about it quite a bit. Oh.
Just think about having more than two parents for robots.
I kind of glossed over it, I guess.
I guess you'd have to have rather large robots to have enough pieces
Yeah,
to take them through.
because you know, in this case, so each one of these is composed of six functional units. So having more than one parent, like I said earlier, it would change the children like a lot. There'd be huge changes in the children. But I did think about it. I decided that because I was reducing the search space, that maybe I shouldn't have as much variation in the parenting. So I decided to go with two parents.
A single parent doing slight mutations to a single robot.
yeah, that's a question I wanted to ask the two of you. You went with crossover and you went with mutation, and I wonder, you know, it's kind of strange to glom onto one and not both, and where you were coming from. You're saying you might want to put some mutation.
It's probably one of the first things I put into that list.
But a fully mutated program is kind of unusual. Where did you come up with?
So for mine, it had been my experience that there are lots of different configurations of weights that produce good weights, and combining two of them together could easily produce a terrible, terrible result. So perhaps one set of weights could be all negative but still perform really well, and another set of weights could be all positive and perform really well, but just relative to each other. And then when you average those together, perhaps they're all 0 and then perform terribly and score about 7 pieces. So for mine, it just didn't make sense to me to do cross mutations between good performing sets of weights, and instead do slight changes to ones that do well.
But Brian, I can't see yours without crossover. I mean, it has to have.
However, if we took it from the standpoint of just rewarding them for moving, maybe in that case, doing purely mutation might be a good thing, because then they would diverge, and maybe diverge positively. So I think that could be a potential solution to allowing them to just simply move.
These little dudes do all right.
Maybe trimming, deleting a few functions.
Yeah, some growths. Right, are there any other questions?
Thank you very much. Right.